Can the gravitational field have its own mass? Somehow it sounds like the cat is biting its own tail, but it's nothing else than to consider, for example, strong magnetic fields around neutron stars when calculating the course of their gravitational field. In this video we will see that a simple energy balance yields something very astounding. Hello and welcome to 6 Dimensions in Color. My name is Schmid and I explain to you Burkhard Heim's worldview in understandable language and with clear examples. In the last video I showed you Heim's assumptions about the geometry of space and the conclusion that space itself must be quantized. What follows now is a deduction of this quantization of space. Actually, what I'm presenting to you here is not Heim's own deduction, but that of one physicist, Florian, which is much easier to explain and to grasp. If geometry corresponds to energy fields, as we have deducted in the previous video, then the thought is near to assume that the gravitational potential of an otherwise empty space equals an energy by E equals mc squared. This means that this field will have its own mass. If we now look on this in the Newtonian way, we must consider both the solid mass and the field mass around it. And this will probably change the course of the gravitational field in a yet unknown way. Imagine a mass particle that will have the mass m0 and the radius r0. And between us and that mass particle will be the field mass, which we call mu of r. Obviously, if we move away from this particle, the gravitational potential decreases, and this must mean nothing else than the field mass, mu of r, being negative. So, the more we move away from this particle, the lower will be the observable mass. And if we take the equation for the gravitational potential, we must insert m of r instead of m0. What we're looking for now is an equation from which we can obtain this total observable mass m of r. For this we must, of course, contain the total energy content of the system. Now we can consider the energy content of the gravitational field in an analogous way like that of an electrostatic field, where the field mass appearing in the negative because its potential is obviously a negative one. Alpha is a field constant for the gravitational field, which equals to 1 through 4 pi times gamma, where gamma is the gravitational constant. The uppercase gamma in the balance equation is the gravitational field strength, for which we may also write lowercase g. At this point, of course, we are only considered a static field with no moving masses. We can integrate this equation and solve for m of r, and then we yield the following. If we have a closer look on this denominator, we can cancel some things out, and then we find something very interesting. If you know where to look, you can find the Schwarzschild, he was German anyway, Schwarzschild radius, I can't pronounce it. You can find the Schwarzschild radius inside here. Most of you will know the Schwarzschild radius from the theory of the black holes. A black hole has an event horizon on which light can no more escape, and the gravitational potential exactly equals c squared. This is the Schwarzschild radius. So with Rs we can rewrite our equation in this way, and now we can plot this as a graph. I've inserted the mass and radius of a proton here, but the course is the same for every pair of elementary particle. Now we see that there is a pole here. And this means something really exciting, because this means below that pole the gravitational field cannot be defined anymore. This pole defines a lower boundary of reality of the gravitational field. And we want to solve for this pole, the radius of this pole now. We take the denominator and set it 0, and for r we set r minus, which is this lower boundary. However, if we solve for r minus, we only get such an expression, which we cannot solve any further. But now we have to consider the following. We have considered pairs of m0 and r0 here. But what are they really? if you look at the curve, we see that the curve approaches m0 at infinity asymptotically. But this also means that truly we will never really measure m0. We will only ever measure pairs of mr and of r and mr. We will never be able to measure the naked mass, if you will. We only ever measure mass and field mass at a certain distance combined. But this means we can take any pair of r and mr, and we are also allowed to take such a pair at a very great distance. This means we can use the limit for r0 approaching infinity to solve this equation. Then Rs no longer matters in the denominator. We can cancel r0 out, and we yield 1/4 Rs for our lower boundary of the gravitational field. Well, isn't that amazing? You can also do this numerically, but you will yield the same results. Heim got the same result with his approach, except for a factor of 4/3, which was the result of a calculation error. This error had no influence on the final results, however. So we have found a lower bound of the gravitational field on the macro scale. And this means the gravitational field structures a mass in the very smallest. It also proves that point particles are a physical impossibility, by the way. All of this we deducted from a simple energy balance from Newton's law of gravity, without superstrings, without space curvature, without quantum theory. Some may say, oh, this sounds too simple, there certainly was some cheating in it. But you can see the deduction for yourself if you like. I'm linking the source of that related article done in the video description. Please don't bother, that is German. So we have found a certain barrier of reality in the very smallest. And in the next video, we will see what this barrier means in combination with the very largest, in 6 dimensions and in color.